There's a few people coming in still, so.
And everyone moves slower the further on the day.
Yeah. All right, good afternoon, everyone. Welcome to the final panel of the day, standing between us and happy hour. Thank you for joining us. We're going to talk about a new topic today. Hopefully you find it practical and thought-provoking as we find ourselves here in New York City. The topic will be ground heat exchanger design with modular reversible chillers. My name is Amanda Schneck. I work for WaterFurnace. I'm a current NY-GEO board member and founding member of the organization. And as I mentioned, I work for WaterFurnace. We manufacture geothermal heat pumps, water source heat pumps, and commercial chiller products. Today's panel, we're going to focus on the growing adoption of modular chiller systems, specifically 6-pipe configurations as an optional design approach for single-plant geothermal systems. Designers and building owners are drawn to these systems for their flexibility, their efficiency, and their ability to simultaneously meet heating and cooling demands. But that versatility doesn't come without trade-offs. With increased capability comes increased complexity, especially when it comes to system operation, sequencing, and control strategy. The way a 6-pipe system is specified, ordered from the factory, piped in the field, and ultimately controlled can fundamentally shape how the building interacts with the ground heat exchanger. These decisions don't just affect mechanical performance, they directly impact bore field sizing, thermal balance, long-term efficiency, and overall system reliability. In the session, we'll dig into the design, equipment, pumping, application, and control options available today, and explore how those choices ripple outward to impact the design and performance of the ground heat exchanger. Our goal is to move beyond theory and into real-world application. What works, what doesn't, and what you need to think about early in the process to get it right. Today, we have an outstanding panel of experts that bring a unique perspective on modular chiller systems. We have Chris Johnson from Trane, Tim Hammond from CCG, Dan Arnold from JW Swanson, and Daniel Cowan from Fynite AE. So we're set up for a well-rounded and insightful discussion, and I'll pass it over to Chris to get us started. Thank you.
Good afternoon, everyone. Chris Johnson with Trane, sales engineer, kind of account manager. We fill a bunch of roles here at Trane. Been in renewables and alternative energy for about 15 years, spread across hydrogen, distributed generation, and a bunch of little things here in between. Background in both business and mechanical engineering. Here, just a quick overview of a geothermal system. I think at this point everybody should be relatively familiar, but it's a good picture because it shows we're 50% inside, 50% outside. The basis of the image is pretty solid. So today we're talking about modular 6-pipe and really how accessible that's made it, some of the challenges that come along with that, and from our point of view, all the changes we can make inside the building. This is a panel of most folks who have stuff that's in the building and how it affects our heat exchanger in the ground outside. So really the most important thing for any sort of heat exchanger design is just your design process here. We start with knowing our building heating and cooling loads. That's really one of the biggest points for me, is just understanding your loads. Then you kind of go through and just work through your heat pump performance, any of the heat rejected, heat accepted from the ground, your thermal properties of your wells so you can understand how fast and slow that heat is rejected and accepted, ground temperatures, and that all feeds back into a feedback loop that you're hopefully simulating. Probably one of the biggest points for me about modular 6-pipe systems is that As you may have heard Gannon talk in the previous session, at Trane we've been doing cascades for a long time. Those cascade systems are large tonnage. They give you 6-pipe performance, but at thousands of tons. Modular chillers really give a huge accessibility to these same system performance at much smaller scales. But with that kind of system performance comes some of the complexity of really needing to understand how the loads and the simultaneous heating and cooling kind of affect your bore field. And at these smaller projects, maybe understanding the simulations, understanding your loads in a little more depth than we might otherwise do on a small project. Just sat through one of the U10 projects and everybody talks 8760, looking at full analysis like you might on an energy project. I think a lot of times that can kind of get lost in some of the smaller MEP projects. So anytime we're dealing with these, especially when you're looking at simultaneous heating and cooling, really understanding that full year energy model, particularly with 6-pipe systems, understanding how much you may or may not be able to downsize your bore field. I mean, that's ideally the advantage of 6-pipe is you're not sending as much energy to or from the field. And so you just need to look at that to help with project feasibility. So a couple other major points here. I'm from upstate New York, so for us, geothermal is really about heating for the most part. So we're always talking about just don't freeze the well, and that happens over a couple of different terms, whether it's peak output, so short-term freezing, field recovery, say a long stretch of days, or your thermal drift over a long period of time. And that's really where all the simulation performance comes down to. The other one is just understanding the system on site, making sure you've got all the right variables in the system so that when these systems go into the field, we don't have to come back later and work on solutions that we've heard about to help trim these fields or deal with runaway temperatures or underperforming systems. And with this, I'm going to hand it over to Tim.
Hello, I'm Tim Hammond with Climate Controls Group. My background is in engineering. Spent the past 20 years working on design of the equipment. At probably about 14 years now, heavily into the modular chiller equipment. And just wanted to talk a little bit about the simultaneous heat recovery versus heat pump. I feel like I should have went before the prior group because we talked about chiller heaters and we're talking about a lot of different terms. And not knowing exactly who the audience was here, I wanted to just clarify some of the terminology. I know as an equipment person, we throw a lot of different things out. And really when we talk about, 6-pipe, we're talking primarily about heat recovery, right? Simultaneous. So what does that mean? You got a base simultaneous, you got a base heating load and a base cooling load, or you're doing some kind of thermal storage. And so, and sometimes the refrigerant circuit in those cases are actually very simple equipment. It's just a straight chiller that's connected to a load, and we're modulating on the water side. And that's, I think, really the beauty of the product is it's simple, it's flexible, and it's scalable, and it really opens up, the ability to put simultaneous systems at lower load levels. So just kind of the key takeaways from, what are we chasing? We're really chasing that purple band. The more purple there, the more efficient the system is, the more we're operating in simultaneous heating and cooling. And then just to distinguish what's a heat pump system, it's where you're gonna have just a dedicated heating mode, dedicated cooling. They're not overlapping that much. So the equipment, generally, I think one of the gentlemen from Trane said this earlier, when we talk about heat pumps, we're talking about reversing refrigerant, so it has a reversing valve in the equipment. And then the key there on the modular equipment is that source loop is isolated from the heating and cooling, so that's why you're not able to get simultaneous out of that equipment. I know there's a lot of different ways to apply the equipment. Just wanted to capture kind of the simplistic approach and say, the building loads aren't changing, right? We're scaling, typically in the modular heat pumps or modular chiller systems, we're scaling, 2 compressors. And I think what's nice about that is, there's a lot of different technologies out there. And it's a little bit like having the internal combustion engine versus the electric car discussion. Is, are you pushing some of the energy back on the production of the system, or is the internal, combustion engine efficiency sufficient? And so there's no right or wrong. It's just what you want for your building. And what I think is nice about the smaller systems, I'm talking about the 20 to 100 ton individual units, is it's really a nice system that can work for a lot of different applications where you have a base simultaneous load. You get a lot of redundancy, and then you're ultimately able to match whatever load diversity you have in the building. And really the impact of the ground loop is just the net difference of your loads. I don't know how this is going to show up on here, so I apologize for all the schematics. But again, on that idea of kind of defining what types of equipment are out there, you hear a lot of 2-pipe and 4-pipe and 4-pipe reversing. And again, not really sure who the audience was going to be here. Really we're talking about the one here in green, which is the 6-pipe simultaneous. So in these systems, they're very simple. It's a straight regular refrigeration cycle, and we're mixing on the water side. And I think that's just the beauty of the modular chiller system, is all we're doing is moving energy most efficiently throughout the building, and really just load matching. And so I think what's convenient about that is it's not an overly complex system. It's very basic. Refrigeration, and I think when we get into some of these discussions, especially whether it's a high lift or whether it's a positive displacement, there's a part of this discussion that has to be, can you build it? Will it last? ASHRAE says 25 years for a water source heat pump system, and you got to be able to service it efficiently and timely. And I think there's also something to be said about the labor that goes into building some of these products. And when, I would say some of the downside to some of the other technologies is, if you're running 2,000 PSI discharge pressures, what's the implications of the labor to build that? I'm not saying it's right or wrong. It's just different approaches to the market. And at the end of the day, we give building owners what they want to really meet their needs. So that's just a little bit more about the 6-pipe simultaneous. You take that mixing of the water, between the source and the heating and cooling loops, and then you scale it and put multiples of those together. And really, you can pretty easily get up to 600 tons. Not saying that's the fine limit. That's just probably the typical limit based on, what's coming out of the factory. But I think 600 tons gives you a pretty broad range of buildings that you can cover. You can also do multiple banks if you wanted to get more sophisticated. But the beauty of this technology, again, is it's simple. It goes through a doorway. It's light. You have replacement options if you want to keep a unit. Keep a unit on site for replacement. All of these units can be easily pulled out and serviced if need be. And really, each module does not necessarily care what the other module is doing. Now, that's not necessarily saying you're going to run it that way, but in reality, since we're only mixing on the water side, there's, the refrigeration system is very simple. And so I think from a troubleshooting, from an industry perspective, it's a highly, it's a highly efficient system. It's friendly to service. It's easy from a manufacturing standpoint, and so it may not be as fancy as some of the other products that were discussed, but I think it is a nice solution. And then just some of the guidelines. Typically, this product is 70 to 140 degree leaving water. Most of these systems are 454B, and then 15 to 65 degree on the chilled water side. And with that, I'll hand it off to Dan.
How you doing? I'm Dan Arnold with J.W. Swanson Associates. Born and raised Buffalo, New York. J.W. Swanson Proud to say family-owned for over 70 years now, which definitely want to make point in that today, especially in today's HVAC marketplace. We're an engineering-based HVAC sales organization, so really take that approach to every job we look at, and bar none, relationship-driven business model. There is a lot of people at this conference today, but it is literally 1 degree of separation, right? Everyone either knows everyone here already, or maybe it's one connection away, and we really all are in this for the same thing, right? Successful geothermal projects, bad ones, whether you're a part of it or not, does no one in this room any good, because word gets out on it, it just doesn't do the industry any good. So it's important that we're all here, and this is a great topic only because if you look at it 5 years ago, the technology has changed, and if you look at it 5 years into the future, technology will change again. So it's great that everyone's here, and Amanda has put this board together because this is one of those areas where things move rapidly. You want to stay with the industry and always stay ahead of the times. I am a licensed PE and CGD. Again, relating this back to the ground loop is really what we're here for. So when we talk about the modular heat pumps and heat recovery systems, there's a lot of ways to skin that. There's 2-pipe, 4-pipe. This is really what we're talking about in the building system itself. Just when Tim got finished talking there, he's talking a lot about 6-pipe, and that's what we're here to talk about today. So just to recap, 6-pipe is you're looking at 2 source pipes, 2 chilled water pipes, and then 2 hot water pipes, which would inevitably feed a 4-pipe system in your building. That's really the core of what we're here to talk about today, but there are a lot of ways to do modular systems, and I just wanted to make sure that was aware to everyone. I have the same picture, the same graphic Tim used, and that was on purpose because that is really what we're here for, is to get that purple area, that simultaneous heating and cooling. That's what really drives the efficiencies on these systems, gets the best benefit for the owner, and really the team in general. When we're looking at application considerations, though, we always want to make sure that we're paying attention to things like system volume. Okay, when we're dealing with refrigeration systems, these are not instantaneous hot water heaters, so we do want to pay attention to that. These are compressorized pieces of equipment. And then loop temperatures. Okay, so there is a wide range, and Tim highlighted that on what this type of equipment can kind of work within. You can do all different kinds of stuff, but thing to pay attention to, just like what Tim mentioned with the high temperature equipment, there's trade-offs. Can you do a 140 degree leaving water temp on the hot water side out of a scroll compressor? Absolutely. Do you sacrifice a little bit on the COP as compared to maybe doing a 130 degree or 120 degree loop? Absolutely. So you always want to pay attention to that, because now that goes back, and we're doing the full story here, they'll go back to Chris, energy modeling. What does that now do to your ground heat exchanger, right? So everything has trade-offs. Yeah, you might be able to satisfy your building a little easier, but what does that do to your first cost on the system? You just always have to take all that into consideration. Retrofits. This is very common, probably comes up much more common than new builds, especially in Western New York. We love our old buildings, and they got to keep that way, and we kind of have to work within those confines to really make things work. So you might be replacing a system that was a 180 degree hot water loop. Do you need that temperature? Okay, this is where we do come back to modeling and really doing your homework on things. Just because what was there doesn't mean it's what was right. A lot of old hot water systems were oversized. I can't tell you time and time again, we're asked for a selection on one of these types of systems, and people are simply trying to just mimic maybe the 2 big boilers that were down in the boiler room before. Well, it's really good to look into that, because maybe one of those was redundant. Maybe you really don't need that much capacity, because that might equate to 10 modules of one of these heat pumps rather than 6. So it's really good to just do your homework, understand what your building needs and what's going to keep it ticking, and not just assume that what was there was right and proper. Same thing with piping arrangements. You might be dealing with an existing hot water system. Maybe it was designed around a 40 degree delta T. Your pipes might be a little smaller than what you need. That's going to lead us right into pumping strategies and how we might achieve and make that building successful. But things that you just definitely have to pay attention to, because again, these aren't instantaneous hot water heaters. They're not boilers that really like these wide ranges of design. And we just want to kind of work within that to really make the system efficient and first cost friendly. A lot of, especially in the K through 12 market, we're seeing more and more where maybe a building is heating only now, and now you want to add cooling. That's very important to know up front, and that's going to fall right into this 6-pipe story. because we do want to take advantage of that simultaneous heating and cooling. But why that's so important is, we want to make sure that ground heat exchanger is sized to, really handle both of those loads. We've been through enough of these where an imbalance is not going to be good. It's not going to equal good longevity for the system. So again, just tying that whole story together, we want to always pay attention to all of that. And then lastly, pumping considerations. This is very important. I mean, we go through this on almost every job, and the only thing I want to stress here is when you are working with one of these systems and laying one out, I just encourage to use your resources. We're a manufacturer rep, so we work really close with our partners. We got a lot of them here today. The Sharks, the Niles, WaterFurnaces, and thank you to all of them for being here. But you want to make sure you're working with these folks because we want to design things that work well with the system that's intended. Making assumptions, especially on systems like this that are, they're not new technology. Things like this have been out there for years now. But maybe it's the first time your firm's working with one. Just use those resources. I think I heard on the panel before us, questions are free. I mean, just ask them. People want to answer that. And you can really get into a jam if you're not following some of these application guidelines from manufacturer to manufacturer. And the biggest thing is just remember, the connected load is not your building load, so these heat pumps do want to be satisfied. And when I talk about pumping considerations, it's just always making sure that that flow is there for both the building side and the heat pump side. And that is also a good segue into the next topic, which is on the controls. So with that, I'll introduce Daniel.
So I'm Daniel Cowan, and I'm the Chief Engineering Officer for Fynite. We are owner's representation firm and forensic engineers. So I've had a meandering career over my time. I did 4 years in the Navy, and then I spent 11 years doing service and construction in the field. And I came to realize that a lot of problems were application issues, and I couldn't solve them as the service tech. So I ended up going back to school at University of New Haven and getting my mechanical engineering degree, and now I'm a licensed engineer in the state of Connecticut. And I did 8 years on design build contracting, again seeing lots of application issues, buildings operating not as they were designed, but built differently. On a personal level, I'm a avid snowboarder and a member of the Orthodox Church of America, so if anybody wants to talk about snowboarding afterwards, I'll be around to talk about that. So I'm going to give you a real world example. There's a financial institution here in New York City. It's a 60-story high-rise tower. They got the top 10 stories of that tower. They have locally hosted servers for trading. They wanted to provide their customers precise, not their customers, but their employees, precise indoor environment, plus or minus a half a degree. So to that goal, they gave them radiant panels in every room, sensible heating, sensible cooling coils on the trading floors, so in case anything went down, we could still cool. And we get a base building VAV system from DX air handlers that are attached to a cooling tower. And there's an image of the chiller room to the far right there, which shows we have redundant pumps and anything, so it's built like a data center on one floor. Let's see. So, where am I? Yeah. So one of the design considerations that the engineer of record took into consideration was a statement in the manuals that said that all systems must be at the same pressure level. And historically, we've always put this place of zero pressure drop on the pump suction. Now, our configuration for this plant was that we drew through all the chillers simultaneously. So we don't pump into the chillers, but we draw through them. And what ended up happening in this case was that because the point of zero pressure drop is on the pump suction and not on the chiller manifold, the pressure drop between all the chillers is significantly different at different flows. So if you have one of the chiller banks, one of the chiller headers at like 90 PSI, there's essentially no pressure drop in the system. But if we're running at 350 PSI on the same exact header at a different time, you could have 3 or 5 PSI difference between what the header sees and what the pump suction sees. So this equalizing line, which is required for equalization, because as the valves blend, all the water is mixing, and you can end up with a volumetric imbalance between the three headers, is required to allow water to bleed back across system to system. So what we're doing to resolve this issue is we're actually relocating that line from the pump suctions, which is shown in orange on the diagram, to the chiller inlet on each of the three headers, so that that same pressure is always on the headers and leads to equal pressure drop across the manifolds. So what we were seeing was erratic flow control over different operating ranges, nuisance trips on flow protection, and most prominently, this was happening during load shifts, when the building went in and out of occupancy. And so one of the things that led to this is we provide 3 hours before and after the DX cooling is on for our occupants to get cooling in their offices. So in case they want to come in early or stay late, they can still have sensible cooling from the radiant panels or the sensible cooling coils. So by the end of that 3 hours, our sensible systems are at full speed and providing nearly all the cooling the space needs. Then DX cooling comes on at 7 a.m. and the load goes to nothing almost immediately because the VAV system's taking over. When the pressure drop across the valves, and there's this assumption that's made that you're gonna have linear flow across your control valves. There's 2 butterfly valves on these systems that control net water flow into the inlet of the evaporator and for the heating and for the cooling needs. So we have butterfly valves on this, and we all know that butterfly valves are not really linear devices anyways, but when the pressure differential across the valve gets great or different, you can have a significant flow variation. So the first graph that's closest to us on this side shows that if you have both valves with a 0.01 pressure drop, almost nothing on them, and they're equal, that even as the valve modulates open, you could have up to a 40, I think that's 40, yeah, up to a 40 gallon per minute decrease as this valve is blending, trying to maintain your leaving water temperature. Our chillers are 54 GPM, so a 40 GPM decrease is enough to cause them to trip out. And if you exasperate that, say like 3 PSI, or versus the 0.1 PSI. So if you have one, let's say your hot water header to net water header is at 3 PSI differential, and your chill water to net water is at 0.01, you could have up to a 200 GPM, or no, 400 GPM decrease on the flow, which would definitely trip out any system. Now this relationship is inverted if the pressure differential is on the opposite way. So if your net water is elevated above your either header, then you'll end up with a flow increase on your evaporator. And the butterfly valves are not very linear, especially like that first 25% range. So you get essentially no flow from the one that has low pressure and a significant amount of flow from the one that has high. So this is a screen capture of the actual system in operation. And what you can see on this is that the flow rates shown here is 96 GPM on the chilled water, 128 on the hot water, and 175 on the net water, which is going to the bore field or going to the cooling tower or whatever source that you're going to be using. And that represents about a lot of overpumping that's happening. You know, given the fact that our chillers are 54 GPM chillers, you can see that we have on the far left side of this, you can see that we have 4 modules running when we really only need 2 or 3 running to meet our building needs. And that's because we're bleeding a lot of water through these to maintain our leaving water temperatures and to get safe operation more staged on. So what we have decided to do is reprogram the entire control logic so that we're leading the control strategy based on flow and delta P versus chasing it with a leaving water temperature. So we're going to look at how much chilled water GPM we need and stage on that many chillers, and then leave it up to the manufacturer to control the leaving water temperature beyond that point once we're in a stable pressure and flow range. So So this brings us back to like the very first presentation in this section that we were going through, where that simultaneous heating and cooling load is critical to identify for your space, because that allows you to downsize your bore field and only use it for what you're supposed to be using for, which is a grounds battery storage and some peak trimming on the shoulder seasons. And I'm going to turn this back over to Amanda for any questions that we may have.
Yeah, we'll start it off with the crowd. If anybody has any questions for our panelists.
Hi, this question is for Daniel Cowan. So I think what you're saying is the way in which the external components to the chiller are arranged. Can you go into a little bit more depth on that? It's like, because you have the 6-pipe chiller plant, whether it be from whatever manufacturer, because you have 3 manufacturers, but if the system isn't set up right, it's going to be chaotic in the system. Can you explain that a little bit better?
Sure. So essentially, the engineer of record has a big responsibility when applying these module systems, right? The manufacturer is going to provide you a system with valves that control the flow through their device and blends to leave up for a leaving water temperature. But we as engineers of record have an obligation to understand the entire system effect, right? What's going to be our peak flow? What's going to be our minimum flow? When's that going to happen? When's the simultaneous heating and cooling going to happen? And we can't just throw it on the manufacturer and say, give me a system that works, because every building we know is a prototype, right? And so we have to include in our sequence of control a detailed enough explanation of how we want to control this flow and how we want to stage on these machines. Because the manufacturer can only start and stop the machine, and if you get a nice reversible chiller with a VFD on it, they can trim down to exactly what you need for a leaving water temperature. But we as the engineer of records really need to specify when we're turning on and off the machines to meet their flow requirements, because the manufacturers provide us the requirements, but it's our obligation to meet those requirements. Does that answer your question?
Yes.
That's great. We got another question back there. Please say your name and affiliation before you ask your question.
Tony from Pratt Institute in Brooklyn. A couple of you mentioned this efficiency of the simultaneous heating and cooling, which I'm just trying to understand it a little better. So if I've got an IT room and the rest of the building, my IT room is always generating heat pretty much. So you're saying that if I can take that heat in 2 of those pipes and then spit out, if I can recover that heat, right, and then either make heat, that's going to be efficient. But if I'm trying to make cool, that's not going to be efficient. So I have 2 questions. So that's, how does that work, is one question. And then we're looking at putting in a thermal energy network and recovering heat from the buildings and sharing it. But if I have a lot of waste heat in a building, it seems to me it's going to put it into the loop, it's not going to be as efficient as if I could use it right in the building if the chiller was right in the building. So is that correct? So, go ahead.
So, on that, so we have several data floors in our building right now, and we're using that heat that's generated by the data rooms to provide reheat and comfort to the space level. So we all know that there's a prohibition against simultaneous heating and cooling, but there's an exemption for that if it's site recovered energy. And so we're allowed to use that and provide a higher level of comfort. Now, when we talk about efficiency in simultaneous heating and cooling, you have to look at the compressor lift, right? So if you want to run just enough machines in your simultaneous mode to meet that recovery spot, and then you want to use something that is on the net water to hot water to make that additional heat that you need. So you're always lifting from like 70 to 140, or you're lifting from 40 to 70, right? So that again goes into the control sequence that the engineer of record needs to provide, saying that I want this many chillers running at these times so that you can minimize that lift. Now, talk about a large story building. 60 stories, and we have our plant on 10 of the stories. So you have that core cooling need in the middle of the building for 50 stories, right? So that's putting it into the loop. In the wintertime, because we're providing heat around the perimeter with our system, we're actually extracting from that loop, lowering the water that's going, and even though it's an economized loop, and it's making 55-degree water for the purpose of economizing, we're able to lower that water down another 3 degrees to like 52 degrees, which reduces the amount of pumping that the whole building has to do, limits the amount of fans that the building's using to do their economizer. And so it ends up being a more efficient system for the whole building because we're able to extract heat and put it to good use and offset the fossil fuel usage that was provided by the baseboard radiation, because radiant heat is a more effective heating source than just, you know, baseboard along the windows. People feel the warmth shining on them, and they're more comfortable at a lower temperature. So I don't know if that answered all your questions, or anybody else want to comment?
All right, anybody else? Got a shy group. Is happy hour?
One last thing I'll say too is that, like, choosing your water temperature is important, right? So 120 degree water with radiant panels is far more effective than trying to make 140 with baseboard. And so, you know, your terminal device selection, like, I go back to like the engineer of record has a big role when applying these module systems, right? Manufacturers are going to provide you a piece of equipment, but it falls on us to really do a good terminal unit design and selection and control as well.
Follow-up question, go ahead.
So a couple of times today, I've heard that and using modeling to set some of this stuff up. And I know eQuest and DOE2 kind of energy modeling. When you guys talk about this modeling on the, either on the well side of the, for the GEO, or as you were just talking, Daniel, which I see is important, like you're saying, these water temperatures on your chillers, to me that has a big effect on your COP. So what kind of modeling software are you talking about, please?
For the most part, the energy modeling software that I was referring to is for kind of just understanding the loads, and they're all based on the DOE2 models. So there's a bunch of different softwares. Trane has one of them. It's the Trace 3 Plus, but it allows you to model your buildings, understand your loads in full 3 dimensions. So those are a lot of times when we're talking about for energy modeling of the indoor loads. There's a different set of software for understanding your loads and kind of your field temperatures over time. But I'm honestly less familiar with those.
But the two models like tie together, right? So if you're using GLP to do your bore field modeling, it needs a file to actually do that borehole calculations from. And that's going to come from your trace or your HAP or whatever you're doing. And it looks at a bin analysis essentially per month to calculate that bore field. So garbage in, garbage out, right? So if you do a poor building model and feed that into a bore field model, that's going to give you oversized bore fields or undersized bore fields. So it all starts from looking at like your load at the building level, and then that feeds into the proper sizing of your bore fields, whether or not you can reduce it by 2 or 3 bore fields because you have simultaneous heating and cooling. But if you're just looking at peak loads, you're never going to find that out. You're never going to get the right sizing of the bore fields.
Can I ask another one?
Please.
Okay, so another thing that I heard today that, and I've been in this field a while, so I've heard lots of times that if we undersize the bore field, it's going to heat up over time, and I think that's been a consistent problem in geothermal, that the field is undersized. What I heard today is that we kind of want to heat up the field before the winter, which I can understand heating it up a bit, but I heard like 90 degrees today. So if I heat my field up to 90 degrees and I'm trying to cool in the summertime with 90-degree water versus 50-degree water or 55-degree water, that sounds like a fairly significant reduction in COP. So, I don't know, comment on that?
So it's how many hours you're at what point, right? So if by September, October, you're at 90 degrees, your cooling hours are much lower. And if you pull that field back down to the 50s before you enter your cooling season, then you're going to be running all summer long at a more optimal temperature. It's not until like the shoulder that you end up with this high elevated bore field. And I think we should also be looking very, very much at like hybrid systems, where if you have a cooling dominated building, that you look at something like a small cooling tower supplemental to it, so that you can charge your field all the way up and get it to that 90 degrees before you enter your heating season, so you don't end up at 45 degrees by the end of your heating season and have a bad COP on your heating side. So it's all about balancing it, and again, like that, starting with that space level load model and identifying that same, like, take any building that's out here in the world that's got a glass facade. In the middle of February, you're still cooling that building because the sun's coming in, shining through the glass facade. If you can move that heat from the south side to your north side, you don't have to put it in the bore field at all. So that's the point of these 6-pipe systems, is it allows you to move the heat more efficiently from the south side of the building in the winter to the north side, so you're not suffering those penalties. And then you add a cooling tower on top of that to peak shave off in the summer, and you get 90-degree water, and you end up with a charged field again. You got a nice thermal battery running into your winter season, and then you run that battery all the way out.
You're giving me a headache. Thank you.
Thank you. Anybody else? Down front? All right, well, we'll be hanging around. Oh, there we go. We got one back there.
Hey guys, Gannon Dubé with Trane. Dan mentioned that these modular products are used quite a bit in retrofits, and that's been my experience as well. But I believe on Tim's slide, he mentioned that in order to get the simultaneous heating and cooling, that the fluids have to mix, which, taking an existing boiler plant and putting geothermal, like glycolated water into that system can really tank the heat transfer on like the airside equipment. And I'm just curious, how do you guys get around that hurdle, and how do you find that balance point between, do we get the benefit of simultaneous at the expense of the loss of heat transfer, or is there a point where we take simultaneous out of the equation and just go with like a 2-pipe or a 4-pipe heat pump machine?
Great question.
I guess I would say that there's plenty of solutions out there. On the equipment side, that's a tough one to answer, to be honest with you. I mean, I think you can do whatever you want, whatever ultimately the system they're trying to sell. So if they want to do, what I call a dedicated source, where they isolate the source loop and just do heating and cooling, I think that's, what we didn't talk about is mixed solutions of modular chillers, right? Which is, you could mix technology and have base dedicated heat recovery modules, right, that are always started up first. I'm not sure how to answer that, because I think it just depends on what they're trying to accomplish on the building side. I don't know if that's a...
Yeah, I was going to say, with so many things we talk about here, it's one of those it depends kind of things, just what Tim was saying. There are a lot of ways to go around that, and depending on the size of the building, maybe you are doing a dedicated machine to do some of those tasks, or maybe you're keeping it in a single bank. It really depends. That's where it's important, like I said before, keeping up with technology and everyone being here, because things do change so fast. We talked about having someone mention variable speed technology. That was a big game changer when we talk about this equipment, because it does allow you to load match a little better with your building. So it is exciting, but it's one of those it depends kind of things.
One of the easiest ways to solve that problem is you just put a heat exchanger between your bore fields and your 6-pipe machines. And so the bore field is the bore field. You interface to it
that answer your question? Okay.
So, Amanda, they gave me the microphone, maybe a mistake. This is Larry Lessard from Achieve Renewable Energy. I have a quick question that might not have a simple answer. For some renewable energy credit programs, I've seen a requirement that heat recovery be excluded from geothermal credits because it's not harvesting heat or discharging heat to the ground loop. And I'm wondering if you've seen equipment that has metering in place to account for that.
I mean, we have BTU meters on all three of our flows, so we know exactly where the BTUs are going at all times, but we didn't apply for any kind of credits or anything like that. We're just doing it because it's nice to report out to shareholders that you're saving so much carbon. So I think that, you know, the additional BTU meters is probably the best way to handle that. I mean, they're not incredibly expensive in the size of these projects.
Yeah, so I think where you're getting at is right, the energy is not, the transfer is not taking place outside, right? It's all being done simultaneously at the equipment. So you do have to find a way to capture that because you are doing it internally, moving heat right from the hot water loop to the chilled water loop or vice versa. So I think, as Daniel mentioned, you know, some way to capture that energy transfer would be important. Just looking at it on paper, you may not see that otherwise. So capturing that simultaneously would be very important.
All right, last call, is that it? All right, well, thank you. Thank you for joining us today. This is the last session. We'll see you guys in the happy hour. Excellent job.
Strung it out to 10 minutes.
Excellent job. You're a fine panelist, Dan. You're welcome back.